we'll talk about recursive sequences. And they're a little different from if you're doing an arithmetic sequence or a geometric sequence, because in a recursive sequence, they have a rule that the sequence depends on previous terms. If you're doing an arithmetic sequence, you can continuously build and build and build from it. It's essentially, adding or subtracting the same value every single time. And in a geometric sequence, it's the same concept. You're going up and you're either multiplying or dividing by the same number every time. But in a recursive sequence, that's not the case. The increase or the decrease in increments is not a constant value, whether it's multiplying, dividing. We're kind of moving up by previous terms, so it becomes more and more important. So it changes a little. So Fibonacci sequence is, this is how it's defined. So they tell you what the first term is and the second term. And you need both of these terms in order to carry out the formula they've given you. So the very first term, maybe you guys can help me do it. The very first term is obviously 1, so that would be considered your T1. The second term is 2, and that would be considered your T2. And then from there, it's up to you to kind of figure it out. So T3. And we can find T3 by using this formula, right? If this value is 3, then we plug 3 into each of these, into this number, and we find out what our term values are. So let's actually go about doing that. Let's say T3. T3 would equal T3 minus 1 plus T3 minus 2. T3 minus 1 would be T2 plus T1. And T2 and T1 are 1 and 2, so we add them together and we get 3. Okay. So essentially what it's telling you is to add the previous terms. I'll do it in red. Add the previous terms and you get the next term, right? So with that idea, T4, we would add the previous terms and we get 2 and 3 here. 5, right? So we continue that pattern. Then we go to 8, change the color, and then 5 and 8 is 13, so it just kind of continues on this way. So this is called Fibonacci sequence. It might be popular for guys, it might not. What we're going to do is there's another one called Lucas's sequence. So we'll see if we can kind of figure out what Lucas sequence is. Now, since it's recursive and you need at least one of the previous values, usually 2, we're going to define what the first and second value are. So what is the first value here? What is our
1.
T1? Yeah, it's just 1. And what's our T2?
3.
Okay, so T2 is 3. So from that information, how do they go about getting the next term? Deduce it from using these two. What do they do with these two terms in order to get 4? What do you think happens?
They added them.
Yeah, let's try. Let's see if this concept works. So 1 plus 3 would give you 4. Okay. So now that we have 4, 3 plus 4 would give us 7. 4 plus 7 gives us 11. Okay, so it works out perfectly. So that's exactly what it is. How do we write this as an equation? Okay. If this is going to be, our new term is going to be, T3 is where we start. Okay. What did T3 do? It took T2 and T1 and added them together, right? So we can write in T2 plus T1. But the problem was this: if we're going to write a formula to build a recursive, we refer to the n term, okay? And that means these can't be defined, because if this is the number, if I'm looking for the t to the 5th, so that would be this guy here.
Would it be the same as the other one?
Yeah, so how did they write the other one? What did they do?
N minus 1 and Tn minus 2.
Yeah, exactly. So you're taking the term just before it, and then you're taking the term 2 before or before the previous one.
Wait, how did these sequences get so famous?
This one, Lucas's sequence, I'm not entirely sure what its applications are, but Fibonacci sequence occurs with like plant petals and like apple seeds. If you cut an apple wide open, you guys ever cut an apple open, and you've seen how they're, I didn't want that to happen. Let's see if I can kind of emulate it. I think with that, or it might be more the golden ratio that this idea happens, but you get like that star pattern.
Yeah.
And if this is a value of 1, then this one here I think is like 1.69 or whatever, and this kind of deals with what the Fibonacci sequence goes with. Actually, I think that one's more golden ratio, but they occur commonly in nature. I think Fibonacci had to do with rabbits breeding. If you have, how does it start? If you have 1 rabbit, you can't obviously get anything. Once you get 2 rabbits though, and they breed with another, you're up to 3, and it kind of just continuously multiplies like this. So there's lots of odd relationships, not odd, but relationships that occur like this, these sequences. And they're not patterns that we really model with a traditional like function or equation. Okay? And that's simply it. So did we build the other one? I can't remember if we did. Yeah, we did. So we built this equation. They always have to be, whatever your equations are for recursive, they have to be in reference to the term number you're dealing with. Okay, so because we're looking for the term number directly before and then 2 before that, we take it as n minus 1 plus n minus 2. And then this operation here could be subtraction. This operation could be multiplication, could be division. There's so many different ways that this could happen, but it deals with previous terms within it. Okay, the golden ratio is another one, but I'll kind of get into that one maybe after. Does that make sense for recursive?